There, welcome back to another 2241 video. This is going to be our example problems for vectors. So let's go ahead and get started with problem number 1 here. So we're given an XY coordinate system and some vectors u and v, and we are being asked to draw the vector sum of u and v. So now let's remember that we're allowed to move these guys around. So let's take u and v, move them over here a little bit. And maybe we'll do the parallelogram rule for this guy. We'll put a point there, the initial and terminals of u and v, and then copy paste the both of them. Actually, I want the tips as well. There we go. Ah. All right, we'll just do it this way. Copy, paste, copy, paste. Move things into place, and we should be good. There we go. Tip, and the final point that we end up at. And here is our vector sum, pointing from the start of u and v there to the end of v and u. This will be u plus v on top and v plus u on bottom. So this also shows you why vector addition is commutative, so you can swap the two terms in a sum around. All right, so that is all that we needed to do for problem 1. Let's now look at number 2. All right, so we're given 2 more vectors, a and b, and we're asked to draw a minus b and b minus 2a. So let's go ahead, copy, paste. We'll paste twice since we need to compute 2 different things. Let's draw a minus b first. So now, remember, for a minus b, we want to think about this as a minus or a plus the negative of b. So we actually think of minus b as being a scalar multiple of b first. So here we'll take this b and reverse it. Now we have minus b pointing in that direction. A little longer. And we can go ahead and do tip to tail. Move that guy over there. And now our ending vector is going to be the vector from there to there. And this is a minus b. That arrow to be a little more arrowy. Minus b. There we go. One thing that might be neat to note is that you can actually pick this guy up again, because you can move vectors around and put him there. And now you sort of have a shortcut for computing the difference of 2 vectors. If you can remember how that works, so the difference of 2 vectors always points from the tip of the second one to the tip of the first one. Of course, you can also always just flip the vectors around and do this tip to tail method if you want. But that's a shortcut. All right, so what about b minus 2a now? Okay, well, we got to move our b and our a around. So here's b, move them down here maybe, and a is right there. And we actually need 2a, don't we? We will copy, paste, and paste again. I'm thinking of this as a, but do it twice in the opposite direction. Points here. And our arrows. that to be in red. Okay, so these are now minus a's. Right there and there. There we go. All right, so what is b minus 2a? Well, as usual, start at the initial point of b and at the terminal point of the last a. That didn't do what I wanted it to. Let's draw it this way. There we go. And the arrow pointing in that direction is exactly what we want, b minus 2a. All right, and that finishes up problem 2. So we're just doing all of this visually. And next up, we're going to do some actual algebra here. So we want the standard form of the vector w that points from the point A in R3 to the point B in R3. So remember our weird notation for vectors. We just want the one that has the first coordinate 0 and the ending coordinate whatever. So that ending coordinate is the coordinates that are the difference between B and A. So what do? Well, W is minus 2. That's our B right there. We want to subtract 2 from that, minus 2. And now we have B's y coordinate is 1, A's y coordinate is minus 3. Remember to be careful with your negatives like that. And then we have for B 1 in the z coordinate minus 4 in the a z coordinate. And if we go ahead and compute those, we'll get our standard coordinates for W. Those are going to be minus 4. 1 plus 3 is positive 4, and 1 minus 4 is negative 3. Okay, so there is W. Pretty straightforward, but we want to make sure that we are getting comfortable with these ideas. Next, problem 4. Let's say we're given two vectors, u, 4, 0, 3, and v with coordinates minus 2, 1, 5, and we want to compute 6 things now. So we're getting a little bit more intense. We want the norms of each and some sums and differences, maybe some scalar multiples as well. So the norm of u, if we remember that formula, it's just the distance formula. 4 squared plus 0 squared plus 3 squared. Okay, that's 16 plus 9, and that's 25, so we get square root of 25 is 5. All right, what about the norm of v? Well, we want square root of 2 squared, or minus 2 squared is 4, 1 squared, 5 squared. So we have here square root of 4 plus 1 plus 25. And that's the square root of 30. You can rewrite this if you want a little bit. Actually, no, you can't. There are no common factors, or no square factors in that number. All right, so there's our two norms. Now what about the sum and difference of u? So now we're doing this algebraically instead of visually or geometrically. So 4, 0, 3 coordinates plus minus 2, 1, 5 coordinates. And if we add these together by coordinates, we have 4 minus 2, 0 plus 1, 3 plus 5, and we get our vector 2, 1, 8 as the sum. All right, u minus v, we have, again, 4, 0, 3, minus now, negative 2, 1, 5. And again, we want to be very careful with our minus signs. So 4 minus negative 2, 0 minus 1, 3 minus 5. All right, what do we get here at the end? We have 4 plus 2 is 6, 0 minus 1 is negative 1, and 3 minus 5 is negative 2. So there we go. All right, now we want to scale v by 3. V is minus 2, 1, 5. And remember that our scalar multiplication, do this underneath, be consistent here, is 3 times -2, 3 times 1, and 3 times 5. So 3 times -2 is -6, 3 times 1 is 3, 3 times 5 is 15. There we go. Last, we have the most complicated one so far. This right here is called a linear combination of u and v. It's linear because it adds in a specific way, and it's a combination because we can't just say it's some addition of u and v. We have twice u and 5 times v, so we call it a linear combination instead. Well, we don't do anything special here. We just put in the numbers and then compute things one at a time. In this case, we can do the scalar multiplications at the same time. So do this one and this one, so they don't affect each other. So we have 8, 0, 2 times 3 is 6, and then -10, 5, and 25. All right, so now what happens if we add these two things together? We'll just do this directly. So 8 minus 10 is -2. 0 plus 5 is +5. And 6 plus 25 is 31. Okay. So now what I want you to notice is that we did all of those computations without thinking about what the vectors looked like at all. I did not need to know what the vectors, what direction the vectors were pointing in order to compute all these things. And that's very good for us because when you, excuse me, when you have 3 coordinates, thinking in 3D space is hard. Now, I said earlier that I want you to get used to doing that, but there does come a point where it becomes too hard to do effectively. Your brain just can't handle all of that information easily. So that is why we have these coordinate representations of vectors, to get things to be much easier to compute. And then at the end, if you want, you can just turn that vector into a picture. All right, so let's move on to number 5 here. What does this say? It says if a vec is this thing, so this is called IJK form right here, and b is this thing, write 2a plus 3b in IJK form. Okay, so here's how this works. We just treat I, j, and k sort of like polynomials. You can think of I as being like x, j as being like y, and k as being like z. And so this is like having, all right, a of x, y, z equal x plus 2y minus 3z, and b of x, y, z, these big multiple variable polynomials, as 4x plus 7z. And then what's a plus b? Well, it ends up being 5x plus 2y, and then plus 4z. Oh, well, that's exactly what we're going to do over here, except we are going to add in twice a and 3b. Okay, so let's do that. A is this thing, and we're going to multiply all of those coefficients by 2. Again, we're thinking of it sort of like a polynomial. So we've got 2i plus 4j minus 6k. And then for b, we've got, we were multiplying that by 3. So we want 12i plus 21k. And when we add those together, we get 2 plus 12 is 14, plus 4j, and then 21 minus 6 is 15. Okay. All right. If we want, we can also write this in coordinate form as the vector 14, comma, or the point 14, 4, 15. if you were to expand ijk as 1, 0, 0, 0, 1, 0, 0, 0, 1, and then use the vector algebra rules, you should end up with exactly this coordinate form right there. I'll leave that to you if you want to do that. All right, almost there. Our sixth problem says find unit vectors parallel and anti-parallel to W, which has this form. Oof, okay, so how do I find a unit vector? Well, I have to write that formula back down for you. Given a vector W, we can compute its unit vector. Hats usually mean unit, which means length 1. And we simply take the vector, compute its norm, and then divide every coordinate of the vector by that norm. So this means W1 divide by W hat, or norm W, W2 divide by norm W, and W3 divide by norm W. All right, and in IJK form, we have the exact same thing. Hold on. W1 divided by norm W, I, plus W2, norm W underneath, J, W3, norm W. Okay, all right, there we go. So we need a unit vector in the same direction and the opposite direction. So we want W hat here. Well, we need, that norm first. Let's get that. Now the norm of W, let's see, we have coordinates 2, -1, and -2. Remember our norm formula, square root of 2 squared is 4, -1 squared is 1, -2 squared is 4. So we have square root of 9 is 3. So all we're going to do here to get W hat is divide all of those coordinates, 2, -1, -2, by 3. So we should have 2/3 I minus 1/3 J minus 2/3 K. There's our unit vector. And then if we want an anti-parallel vector, we can just flip this vector around. We want an anti-parallel unit vector. So minus 2/3 I plus 1/3 J plus 2/3 K. All right, and so now we can say that W hat is parallel to W, and minus W hat is anti-parallel to W. So we're done. All right. Last problem, and probably the most difficult one, is we want to actually do a physics problem. I mentioned this one was going to come up earlier. So we want to find the tension vectors and forces in this diagram. So we have a mass of 100 pounds hanging off of a string, which then splits into 2 strings that are attached to the ceiling at these angles. All right, so what do? Well, we use that our resultant force is the opposite of the force of gravity. And then we can do some trigonometry here. So let's see how this works. We take our mass of 100 here, shift this up a little bit, and we put in a vector pointing down, and this will be called our gravitational force. Maybe we'll call it G. So 100 pounds is that gravitational force. All right, so what is the resultant force on this block of 100 pounds? It should be 0. So the idea is that this block isn't moving, and so if you add all these vectors up, there should be a resultant vector of 0. So not moving. And that implies the final vector equals 0. But we can still write down that formula for the final vector, the total force is, well, it's T1 plus T2, because that's what we get here. T1 plus T2. And then plus that vector G. All right. So what we really need here is we want the components of these vectors. All right, so that's why they give us these angles up here, 50 and 32. So if we're looking at T1 and T2, and we're saying this thing isn't moving at all, well, I've got, again, an implicit XY coordinate system here. X, Y, let's just make it like that. And so we should have that the X coordinates, the X components, I should say, of T1 and T2 are the same. So the X components, so T1X and T2X, we get another equation here. So the total force in the X direction is the sum of T1X and T2X. But yet again, we're going to remember that this is equal to 0 because the thing is not moving. All right, and similarly, we can write down an equation in the y direction. So this is called decomposing a vector into its coordinates, or into its components along the axes. So we're going to have now T1y plus T2y. But now we have g, and so plus gy. I didn't write down the g up in this first one because we know it's 0. G points straight down. But now we can figure this out. So we want the components of these tension vectors. So what do we do here? This is 0. Okay, so G is known. And okay, we want to compute these guys first. So I'm going to redraw the diagram a little bit, and we'll see what's going on here. So given, let's say, T1, vector T1, and that component in the x direction, T1x, we can draw a triangle. And remember, that triangle had this angle 32 up here. And so by the opposite interior angles theorem, if you remember what that is from geometry, we also have 32 degrees down here. Okay, well, if we want this number, the length of this arrow right here, T1x, we have a triangle and an angle, and this is the cosine of that angle times the total of that T1. So it's getting a little more complicated, but bear with me. T1x equals the size of T1 times the cosine of 32 degrees. Okay, and similarly, we can write down the T2x as the norm of T2 times the cosine of 50 degrees, except negative. Why is that? Because if I look back at my diagram, oh shoot, I mixed that up. T1 should be negative and T2 should be positive. So let me switch this diagram a little bit. Apologies. And hopefully that will make things a little better here. 2x. And we can move this around. T1 is in the negative direction, and T2 is in the positive direction. But now we know why that is. Oh, and I mixed up the angles as well. That would be bad. All right, so cosine 50 degrees, cosine 32 degrees. There we go. All right, so now you've just learned how to correct a mistake. All right, so now we know that the sum of these two things is equal to 0. Next, we also have T1y. Now, note that both of the tension forces are pointing upward right here. And so these are going to be positive terms. We have norm of T1. And then for the x direction, we use the cosine. For the y direction, we're going to use the sine. This is T1, so we'll use 50 degrees. And for T2y, we'll use the sine of 32 degrees. All right, and then G, y, is just going to be minus 100. As we see, it's pointing directly in the negative y direction, and it has size the same as the mass of the object. All right, so now what we have is our equations over here, right here. You can think of this as a system of equations. And what we're looking for is these norms. These are the forces of the tension vectors. All right, so once we find those norms, we will have found the vectors T1 and T2. Okay, so let's see, we've got T1x plus T2x equals 0, which means that T1x equals the negative of T2x. Let's just write this down. We want this. So T2 cosine of 32 equals norm T1 cosine of 50. Don't worry too much about that negative sign right now. I mixed up some coordinates with you, and we will deal with that later. The other thing that we have, though, is norm T1 sine of 50 plus norm T2 sine of 32 equals 100. And so now we have a system of two equations and two unknowns. The unknowns are the norms. And we can do some substitution. Let's see, how are we going to do this? Well, maybe we solve for T2 right here. So we're going to do norm T2 equals cosine of 50 degrees divided by cosine of 32 degrees times the norm of T1. And we'll go ahead and substitute that right in there. So we get norm of T1 times the sine of 50 degrees plus norm of T1 times the sine of 32 degrees times the cosine of 50 degrees divide by the cosine of 32 degrees. Okay. Again, I realize we're getting complicated, but we will get through this. And in fact, we can simplify things a little bit here. Note that we have sine of 32 and cosine of 32, so we could rewrite that as the tangent of 32. And then we can factor out this T1, which we need to do anyway. So we've got norm of T1 times the sine of 50 degrees plus the cosine of 50 degrees times the tangent of 32 degrees. And that's equal to 100. So we can go ahead and divide by all of this mess on the other side. And we get 100 divided by sine of 50 plus cosine of 50 times the tangent of 32 degrees. And that is our tension force in the T1 direction over here. Now, we only solved for one so far. I'm going to leave the other one to you guys as practice for this problem, but then you'll see some more problems like this in the homework. All right, and that is our examples video for vectors.